For decades, scientists have told Californians a comforting story. The San Andreas Fault has a section that is safe, a stretch of ground that cannot produce a major earthquake, a built-in barrier that will stop the big one from tearing the state in half. That story was built on decades of careful observation, mathematical modeling, and the fundamental physics of how faults behave. It was the bedrock of California's earthquake hazard assessment. That story is now in doubt. 59 earthquakes have hit the San Andreas Fault in just 6 days, running at nearly 7 times the normal rate. The swarm is centered beneath Pinnacles National Park in central California, on the exact stretch of fault that geologists have spent decades describing as harmless. The fault has been shaking almost continuously since last Friday. It ran through the weekend. It escalated on Tuesday morning. And it is still producing events. Nobody has been hurt. Nothing has been damaged. No agency has issued a warning of any kind. On the raw numbers, this sequence is small. The largest event would rattle dishes in Hollister and go unnoticed in San Jose. What makes it worth paying attention to is where it happened, on the one section of the San Andreas that is not supposed to break at all. 4 years ago, researchers pulled 4 meters of rock from 3 kilometers underground on this same fault. What they found quietly demolished everything scientists thought they knew about this section. More than 100 major earthquakes preserved in that small stretch of rock. Earthquakes that should not have happened according to the old model. By the end of this video, you'll understand why 59 small earthquakes in a week matter, why the creeping section of the San Andreas is not what we thought it was, and what it means for millions of Californians. Let's start with what actually happened. The San Andreas Fault has been producing earthquakes almost continuously since last Friday. And the place it has been doing it is the one stretch of that fault that geologists have spent decades describing as harmless. That's not an exaggeration. The official hazard models treated this section as a barrier, not a source of danger. The swarm is centered beneath Pinnacles National Park in San Benito County, Central California. It began on Friday, August 7th, with 2 magnitude 3.2 earthquakes about 78 minutes apart. It did not stop. It ran through the weekend, escalated on Tuesday morning, and was still producing events yesterday. This is not a normal sequence. In the tightly drawn box that contains the main cluster, the catalog now holds 59 located earthquakes across 6 days. That number is a floor, not a measurement. A great many small earthquakes are recorded on instruments and never published at all. So whatever this swarm actually did, it did more of it than the numbers say. Here's what that means. Central California shakes constantly. To know whether 5 days of earthquakes means anything, you have to know what a normal week looks like, in the same box on the map. Between January 1st and August 7th this year, 218 days, and that same area produced 313 located earthquakes. That is 1.44 earthquakes per day. That is the baseline. That is Pinnacles being Pinnacles. The swarm produced 59 located earthquakes in 6 days, 9.83 per day. The fault is running at roughly 6.8 times its own background rate. On Tuesday morning, the sequence produced a magnitude 3.94, the largest event there in almost 15 years. The depth was 4.62 kilometers. 85 seismograph stations reported it. Within 3 minutes and 33 seconds, 3 more located earthquakes followed. Magnitudes 2.57, 2.60, and 2.14. The largest event to follow was a magnitude 2.66 about an hour and 50 minutes later at a depth of just 500 meters. The shallowest significant event of the entire swarm. Here is the first thing that is strange about this sequence. It got bigger as it went along. A classic main shock and aftershock sequence peaks immediately. The big one hits, and everything after it is smaller and less frequent as the fault settles. This one opened with 2 magnitude 3.2s, ran for 4 days, and then produced its largest earthquake. That is backwards. That is the signature of a swarm, a sequence driven by something progressively loading the fault, rather than by one patch breaking and the neighborhood adjusting. The second strange thing about this sequence is its shape. If a single stuck patch of fault breaks and then adjusts, you get a tight ball of earthquakes around one point. That is not what happened here. The activity resolves into 3 separate clusters spread along roughly 35 kilometers of the fault trace. The main cluster sits 4 to 8 kilometers northwest of Pinnacles, at depths between 300 meters and 5.5 kilometers. A southeast cluster sits 7 to 11 kilometers the other side of Pinnacles, deeper 4 to 8 kilometers down. And a northwest cluster is deeper still, 6 to 12 kilometers. 3 clusters, 3 depth ranges, overlapping but not identical days. That distribution is far more consistent with something moving along the fault than with one stuck patch failing in place. To understand why this swarm matters, you need one number. The San Andreas Fault, over geologic time, slips at 34 millimeters per year, give or take 3. That figure comes from both geologic mapping and satellite geodesy, and it is about as solid as anything in this field gets. It is the rate the plate boundary demands. The Pacific Plate and the North American Plate are grinding past each other at that rate, year after year, century after century. The creeping section slips at 26 to 33 millimeters per year right now, continuously measurable with instruments planted across the fault trace. Those two numbers are almost the same, which means there is essentially nothing left over. On a locked fault, the difference between the plate rate and the observed slip rate accumulates as elastic strain in the rock. And that stored strain is what a large earthquake spends. On the creeping section, that difference is close to zero. There is no strain bank, there is nothing to spend. That single arithmetic comparison is the entire scientific basis for calling this segment safe. It is the reason the official California hazard model, the third Uniform California Earthquake Rupture Forecast, was controversial when it included a through-going rupture crossing this segment. That branch was added by mathematical necessity rather than by evidence. Nobody had ever found a trace of such an earthquake actually happening. Paleoseismologists dug trenches across the central section, looking for ruptures that had broken the surface and found none in the last 2,000 years. But the fault has not been entirely silent here. 1949, magnitude 4.7. 1951, 5.0. 1986, 4.8. 1988, 4.7. 1995, 4.9. In August of 2011, magnitude 4.64, about 600 meters from where Tuesday's earthquake nucleated. By that record, a magnitude 3.94 here is unremarkable. 61 earthquakes of magnitude 3.5 or greater have been cataloged in this box since 1990, roughly 1.7 a year. Uncommon, but not rare and not unprecedented. The fault has been busy the entire time we have been watching it. The rock spires that make Pinnacles National Park worth visiting are the remains of an ancient volcanic field. They are only half of it. The other half sits near Lancaster in Southern California on the far side of the fault. They were one volcanic field. The San Andreas cut it in two and carried the halves apart. The separation today is roughly 314 kilometers, accumulated over about 23 million years. This fault is not a crack. It is a machine that has moved half a volcano the length of California. The part of it, under Pinnacles, has been chewing through moderate earthquakes on a generational schedule the entire time we have been watching. Everything I have told you so far says this swarm is nothing. Now, here's the part that does not fit. At Parkfield, at the southern end of the creeping section, there's a hole in the ground 3.2 kilometers deep that was drilled directly into the San Andreas Fault. It is called the San Andreas Fault Observatory at depth, and it was built to answer what an active fault is actually made of. It took years to drill, millions of dollars to fund, and the cooperation of scientists from around the world. In 2022, a team led by Genevieve Coffey, then at Columbia University's Lamont-Doherty Earth Observatory, published a study in the journal Geology based on cores pulled from that borehole. They analyzed a band of badly disturbed sedimentary rock lying between 3,192 and 3,196 meters below the surface. 4 meters of rock. When a fault slips in an earthquake, friction along the slipping surface spikes the temperature by hundreds of degrees for a moment. That heat chemically alters organic compounds in the surrounding rock permanently. Measure how far the chemistry has been driven, and you can back calculate how much the fault moved, and therefore, roughly, how big the earthquake was. The method was developed by two of the study's co-authors, and had already been tested on faults in the northeastern United States, in Alaska, and offshore Japan. Those 4 meters of rock contain the signatures of more than 100 earthquakes, and in most of them, the fault moved more than 1.5 meters, 5 feet. Slip of that size corresponds to an earthquake of at least magnitude 6.9. The scale of Loma Prieta in 1989, or Northridge in 1994. The authors note that many of them could have been larger because the method for estimating magnitude from slip is still being refined. A second technique, potassium argon dating, exploits the fact that frictional heat drives argon out of nearby rock and resets the radiometric clock. Those reset ages came back as young as 3.2 million years. That is an upper limit, not an age. It is the oldest they can be, not the youngest. Coffey has said publicly that some of these ruptures could have happened as recently as a few hundred or a few thousand years ago. More than 100 major earthquakes preserved in 4 meters of rock on the segment of the San Andreas that is not supposed to be able to produce one. This is where the story gets contested. The way this finding has been repackaged online is not what the researchers said. Some headlines suggested that the creeping section is actually a ticking time bomb. That is not what the science shows. Coffey's own framing is careful. Her line is, "This means we can get larger earthquakes on the central section than we thought, and we should be aware that there is this potential that it is not always just continuous creep." She is not saying the big one is imminent. She is saying the old model was incomplete. Morgan Page, a seismologist at the United States Geological Survey and a co-author of the official California Hazard Assessment, put it more bluntly. She noted that the creeping section is a very difficult place to do paleoseismology in the first place, because the constant creep erases the evidence a trench would look for. And on the finding itself, If this holds up, this is the first evidence of a big seismic rupture in this part of the fault. Page also acknowledged the consequence that if a large earthquake can tear through the creeping section, it becomes possible, inner framing, remote, for a rupture to start at the southern tip of the San Andreas, run through the middle, and continue to the northern end. Then there is William Ellsworth, the Stanford geophysicist, who has led research at the drill site. His point is the counterweight. His line, most earthquake scientists think these events happen rarely because tectonic strain is not accumulating at significant rates along this segment, if at all, at the present time. Read that carefully. He is not disputing the evidence in the rock. He is saying something narrower and more important. A fault releasing its strain by creeping is not right now banking the strain a great earthquake would need to spend. What the rock core records is what this fault has done across geological time under conditions nobody can reconstruct, not what the fault is doing this month, which disposes of the claims circulating alongside coverage of this swarm that a magnitude 3.94 at pinnacles means the big one is coming. It does not. A moderate earthquake in a shallow swarm on a creeping fault does not measurably change the probability of a great California earthquake. Stephen Cox, one of the study's co-authors, said it directly. People should not be alarmed. Building codes in California are now quite good, and work like this exists to figure out what the biggest possible event is so everyone can prepare. Both things are true at once. This swarm is almost certainly nothing, and the fault it is happening on is not the fault we thought it was. The creeping section is not a barrier. It is a description of how 150 kilometers of the San Andreas is behaving at this moment in geological time. 4 meters of rock from a borehole at Parkfield say it has behaved differently before. To see why that matters in practical terms, follow the creeping section southeast to where it ends. Parkfield, California, is a town of about 18 people that is arguably the most heavily instrumented piece of ground on the planet. It sits exactly at the transition, the point where the creeping section hands off to the locked San Andreas. Parkfield generated moderate earthquakes, magnitude 6 or thereabouts, in 1857, 1881, 1901, 1922, 1934, and 1966. Average interval, about 22 years. That is close enough to a schedule that in the mid-1980s, the Geological Survey formally predicted the next one would arrive before 1993. They wired the entire area with instruments and waited. It did not come in 1993. It came in 2004, 38 years after the previous one, more than a decade past the outer edge of the prediction window. And when it finally ruptured, it broke in the opposite direction from the previous events. That failure is one of the most useful things that ever happened to this field because it ended the idea that faults keep appointments. There is one more reason Parkfield matters to the swarm. Slip in the middle of a creeping segment transfers stress to the ends of that segment. The northern end is San Juan Bautista, where the 1906 San Francisco rupture terminated. The southern end is Parkfield, where the fault locks up and continues into the Carrizo Plain. The reach that produced the Fort Tejon earthquake of 1857, an event estimated near magnitude 7.9. So any accelerated slip near pinnacles incrementally increases the load at both terminations. The size of that effect is tiny. It happens continuously whether or not there is a swarm, and no responsible reading of this data makes Tuesday's earthquake a trigger for anything. But the mechanism is real. There are 3 things worth watching over the next 2 weeks, and all 3 are answerable with public data. The first is whether this patch delivers something larger. The 2011 earthquake, magnitude 4.64, sits 600 meters from Tuesday's hypocenter. This patch's history runs to magnitude 5.0. The sequence was still active at a reduced rate yesterday. Whether the magnitude 3.94 was the peak or foreshock to something bigger can only be answered looking backwards, but the catalog will answer it within days. The second is the creep meter record. The most likely explanation for this sequence is a shallow creep transient, an episode where a stretch of the fault slides faster than its long-term average for days to weeks, loading the small stuck patches embedded in it and making them fail in order. That would explain the 4-day buildup, the spread along 35 kilometers of strike, and the shallow depths all at once. It is also testable. This segment has been monitored by creep meters and alignment arrays for more than 3 decades. If a creep event is confirmed for last week, the swarm has an explanation. If the creep meters show nothing, the alternative, the locked patch inside a creeping fault keeping its generational schedule, gets stronger. The third is direction. That southeast cluster, 7 to 11 kilometers beyond pinnacles, was active on 3 separate days. Whether the sequence stays where it is, dies out, or walks down strike toward Parkfield is the single most informative thing the next 2 weeks of catalog data can show us. So, what's the bottom line? 59 earthquakes have hit the San Andreas Fault in 6 days, running at nearly 7 times the normal rate. The swarm is centered on the creeping section, the part of the fault that scientists have long believed was incapable of producing a major earthquake. New research from a borehole at Parkfield suggests that assumption might be wrong. 4 meters of rock from 3.2 kilometers underground contain evidence of more than 100 major earthquakes on this exact stretch of fault. Earthquakes that should not have happened according to the old model. Both things are true at once. This swarm is almost certainly nothing, and the fault it is happening on is not the fault we thought it was. A moderate earthquake in a shallow swarm on a creeping fault does not measurably change the probability of a great California earthquake. But the rock record says this segment has produced major earthquakes before. The creeping section is not a permanent barrier. It is a description of how 150 kilometers of the San Andreas is behaving at this moment in geological time. And the rock record says it has behaved differently before. Seismicity is a measure of release, not a measure of danger. The part of the San Andreas that shakes constantly is the part that cannot hurt you. The parts that can kill tens of thousands of people do not shake at all. The southern San Andreas and the San Jacinto have been assessed at a 1,000-year stress high. The Coachella Reach has not produced major earthquakes since roughly 1680. 3.5 centuries of quiet on a fault that moves at plate rate. Put those two facts side by side. 59 earthquakes in 6 days on the creeping section is strain leaving the system. 340 years of silence on the Coachella Reach is strain entering it every day without release. So, what do you actually do with information like this? If you live in California, know which fault is closest to you. The USGS maintains detailed fault maps through the California Earthquake Authority. Take 5 minutes and find out whether your home, workplace, or your kid's school sits on or near a mapped active trace. Have a plan. Know where you would go if an earthquake struck during the day, during the night, on the weekend. Know where your family would meet if you were separated. Designate an out-of-area contact who can serve as a central point of communication. Build a basic emergency kit. Water, non-perishable food, medications, flashlights, batteries, a portable phone charger. Keep it somewhere you can grab quickly. Secure your home. Strap your water heater to the wall. Bolt heavy furniture to wall studs. Move heavy objects to lower shelves. Get Shake Alert alerts on your phone. Download the MyShake app or ensure wireless emergency alerts are enabled on your phone. If this helped you understand what's happening beneath California, hit that like button, because it helps more people find real, honest coverage instead of the exaggerated stuff. Subscribe so you don't miss updates on this developing story. Drop a comment. Are you in California? Have you felt any of these quakes? And if this helped you, check out my video on the Philippine Fault earthquake. Stay informed. Stay prepared. I'll see you in the next one.